here. We're going to do the ignore version, but we'll see it here in a minute in simple DS. Yes?
I was wondering, in your model, do you use idealized integers for those tags? And if not, how do you handle wraparound?
Yeah, we're going to use nats. So, yeah, we're going to use nats. I think, so we have versions of the systems that use positives, right? Which is a binary representation. But it turns out that even a binary tree to represent a number is much slower than machine arithmetic. So you can always, in extraction, say like, look, I'm willing to believe that my counters don't overflow, right? If that's something you're comfortable with, you can always do that, and then numbers are faster.
So if your system runs for years, don't you kind of guarantee that you're going to run into trouble later on?
It depends what you're doing. 2 to the 64th is a big number. There's some trade-off there, but yeah, it could totally happen, right? It increases the trusted computing base. And so we should be very paranoid about that, right? We should be scared anytime we do extraction tricks. We should think twice. On the other hand, there's always trade-offs. If your system is so slow that nobody uses it, then your verification hasn't helped anybody. So is it better to take on, some guilt and some shame of doing extraction hacks to get a runnable system that's faster, but people actually use? It depends what the system's used for. Yes?
Is it possible to implement unbounded positive numbers with just tries with machine words as limbs?
Yeah.
I think would be faster than just the bitwise try that Pause is.
Yeah.
But would be correct in extraction.
So Maxime was doing this, right? Is it out? Or
for the 64 bits, it's in the works.
Yeah.
There's already a version that exists.
So this is.
But you're still required to do the extraction hack because the extraction doesn't
know about it yet.
Doesn't handle it well.
Right. So this is something that is going to happen, right? These people are going to do this kind of stuff. It will happen. That's not really our core focus here, but these are good questions, right? We should be aware of the TCB. We want to think about the TCB in everything we do. Okay. So in a second, we're going to switch and look at a functor from system to systems, right, that is going to transform a system into one that tolerates shuffle steps. We're going to take a system design for ideal step and build one that tolerates shuffle steps. But I did just want to quickly look at the dupe semantics. So did people get this done last night? This one is not too hard. But I did want to point out a difference between what I showed on the slide and what I actually think the kind of the right way maybe to do this is. So this is actually just like the shuffle step semantics, right? It's actually simpler. So what did I do differently? I see people nodding. Do you have a confident answer? It's almost the same as shuffle step. But I also, I added this new kind of failure, this new kind of fault, which is message duplication. What's different? How does this encode duplication?
You leave the messages unchanged.
Yeah, so remember when we did shuffle step, here we did remove one, right? We took a message from the network, and in the world we stepped to, we removed one copy of that message. We don't want to remove all of them because there could be duplicate messages, identical messages in the network. But we're going to say we delivered this one. That's what shuffle step does, and here it removes one, right? But here in dupe step, all we did is say, well, just don't remove it, right? And that's it, right? So now, just because you delivered the message doesn't allow people to conclude it's not still in the network. And so, what's going on? Why does this make a difference? In a proof, where does this matter? It matters, basically when you're doing the proof, what you're trying to show is that the conclusions that a node's handlers draw about the world when it receives a message are valid. All a node can do is get inputs and get messages. And based on those inputs and messages, it's going to make decisions and take actions, based on some conclusion, right? I believe the fact I got this message means that this other node really is, the leader right now, and therefore I should do what it asks. And what we have to prove is that when the node makes that decision, that other node really is the leader, right? Because from the the verifier's view, right, we can see the whole system. We have to show that what the nodes think is happening is actually right. So it's really like inversion, right? When the node gets a message, it's saying, well, the fact I got this message means something about the state of the universe right now. And based on that conclusion, I'm going to take certain actions. So here what's happening, right, is that nodes can no longer conclude that because they got a message, that it's no longer the network. Whereas in shuffle step, they could draw that conclusion, right? If they got that message, at least there's one fewer of that kind of message in the network. Okay, so we have all the semantic stuff down here. I just want to really quickly, before we jump into Verity code, show this simple version of a system transformer, right? So when we switch to Verity here in a minute, we're going to see a different way of doing that, and I think it's good to see kind of both. Here we're going to do it as a functor. In Verity, we're going to use type classes. So here we have seqnum base, right? So we're going to do the same kind of thing. We have a module that gives sort of the base definitions. We're going to and then we're going to take that, we're going to wrap it in the handler, right? The functor that gives us back the handler monad for those types, and we're going to use that when we define our handlers. So here, when we do sequence numbering, the types of input and output, the interactions we have with our external clients remain unchanged, right? So if I wrap a system, if I transform it to have sequence numbers, its input and output types don't change. They're identical, right? Everything's still fine. And I have the same set of nodes. So the sequence numbering transform doesn't change the number of nodes operating in our distributed system. Now here I did something that is bad, right? So basically what I'm doing is we have the state for the sequence numbering system. Essentially it includes the state for the underlying system, right? Whatever the underlying system state was, we're going to keep a copy of that. We're going to call it data. And we have two other things, right? We have an internal counter for ourselves that lets us know what's the highest number message I have sent so far. So that when I send messages, I can give them fresh sequence numbers. And we also have this scene map, which for every node in the system tracks the highest numbered message we've seen from that node so far. And what we're going to do is, if we see a message from a node, right, that's past this threshold, we're going to drop it because it's not the next message. And acting on that message would mean that the system that we're wrapping would be getting a message it shouldn't, right? It's getting a message out of order. And we don't want that to happen. So we're going to drop things out of order. But this is bad. Why is this bad? And maybe somebody who hasn't spoken up yet. Who among you is feeling courageous and brave? It's not early morning, so I know people aren't asleep. Why does this look bad? Yeah.
Unbounded buffers to keep track of everything you see.
Yeah, so that's a huge problem, right? Right? I'm not just keeping a counter, I have a function. I'm going to update it, right? I'm going to compute a new closure every time. It also means that I can't serialize a state, right? Because scene is going to be opaque. It's a function. So I can't use like OCaml Marshall or something we'll talk about tomorrow, this library Cheerios. Cheerios is for serialization. Yeah, it deserves a groan. Right, so there's, okay, so yeah, so that's not ideal. And this is just a bad comment. Then messages, right, are just, they're going to have the same content as the underlying system's messages, but we're going to slap on the sender, because our semantics actually doesn't include the sender in the packets. And the receiver is going to have to know who it's from because they're tracking the biggest number they've seen from me so far, right? And we're going to give it a fresh ID, right, a unique ID. Okay, so that basically gives us the types for the system.
May I ask a little clarification? In that you only have one fresh counter, so if I'm sending messages to two peers, they can't both get segments of the numbers.
Oh yeah, this might just be wrong.
So maybe you want like a function there too, where X number for each.
So this is a great point. So we're going to look at sequence numbering in Verity, which this is, everything in Simple DS is kind of modeled off of that. Now, you might wonder why this could be wrong, right? Because there must be a proof for it. But the thing is, if you go down to where the proof should be, it says mini project. And it encourages you to go look at the Verity version. So I think you actually might be right. I think this might have just been, editing faster than thinking, which is a bad thing to do. So yeah, there's no way this could work, right? You need to, for the recipient, you have to tag it uniquely. That's totally right. Yeah. But anyways, okay, so the point of this is to give you a feel for how to transform systems. This shows you how to do it. And because we're verifying it, we won't be able to finally make a mistake. And then here we're at the handlers, right? And so these just do exactly what we said earlier. We have an action to ship a packet. And basically all that does is we get the current state. We want to send to the destination of the packet from the underlying system a message where we take the current unique ID, and this now, right, should be the unique ID for that destination. And we just wrap the message and we tell them who the message is from. And then we update our state to bump that counter, right? And again, as we pointed out, right, we should actually be bumping it for the recipient. And handling input also basically, is going to do the same thing where we just are wrapping what the underlying system does, right? We're trying to simulate that system. So when I get an input, I'm just going to run the handler for the underlying system, right? And then I'm going to send out the packets that it wanted to send, right? So when I handle input from the underlying system, I'm going to get back packets for that system. So when I call ships, it's going to wrap them with that ship action we just saw, and I'll send outputs which don't change because the input and output types aren't any different. And then we handle a message. It's also very similar, right? When I get a message, what I'm going to do is I'm going to unwrap it, right? Because the message type is different. So I'm going to take out the message that was, of the type for the underlying system, an S message. And I'm going to pass that to S's message handler. I'm going to get back some new state, some new data for the underlying system, some messages to send, some outputs to send. And then I want to update my state to mark the fact that I got this message, right? And then I'll send out the new messages and send out the outputs. Okay, so after the lecture, I'll add a little bit of a little bit to the README. But when you want to prove it, what we'll say is like, hey, there's a commented out specification for what this system should do in seeknum.proof. That's there right now. And we'll say, currently, the implementation in seeknum doesn't satisfy this specification. Update it so it does. But what I want to point out here, right, is that the spec is actually very simple. So, right, what this is saying at a high level, what we want to show is that any trace that you could get in the wrapped world, you also could have gotten. So once I wrap a system, right? Sorry, I should back up and show you the definitions up here. Right, so we're defining another functor. Right? So we defined a functor for seeknum that actually gives you back a transform system. Now we're defining a functor to transform proofs about a system. So if you give me an original system, I'm going to construct the wrapped version, right? And then I'm going to get the semantics for both the original system and the wrapped system. And here what we're doing here for this spec is we want to show that we don't get any extra behaviors, right? That is, the traces that I can have in the wrapped world are a subset of the traces I can have in the ideal world. Actually here it's dupe and shuffle, but you get the idea. So basically we don't add any extra behaviors, right? So if I knew all the behaviors in the original system were safe, then all the behaviors in the wrap system are also safe, right? And what that means is that a developer can, if they do a proof about their system in a friendlier semantics, they show some trace, they show all the traces that it can ever possibly reach are safe. We know that all the traces that the wrapped version reaches are also safe. And this is, a regular simulation proof, sort of a refinement. Okay, and there's some stuff down here at the bottom, suggestions for key invariants that I think will be useful. And I did want to make one other comment about semantics before we moved on. I think that there was some confusion yesterday when we got to the, we were doing the counter system. And somebody made this point that like there was a moment in time when, you know, sort of like, because we looked at the handlers, right, for counter. Right, so like here we have the message handler. And what does it do? Well, it increments its state, and then it sends, you know, backup will send primary an ACK message. Now the thing is that this is an illusion, right? This is misleading, and I wanted to be very clear about this. You know, there is no in-between here. Why is there no in-between here? There's no state of the world that actually corresponds to this point right now. Right? The semantics will never reach a world that's in between doing the increment and sending the message to the primary. Why is that?
The monad?
Yeah, so we run the full handler. Right? You do the handler for handling a message. Right? And when the full handler is done in the semantics, then you update your state. Right? There's no update to the state in between. So if we go back to the network semantics, right? I run handle input. I don't see any intermediate state. I run handle message. Right? I don't see like the point where I've inked, but I haven't sent yet or something. Right? That's never represented in the semantics. So the semantics assumes that handlers run atomically, right? Like either the handler completely runs or it doesn't run at all. There is no partial way, there's no halfway through a handler from the semantics perspective. So this means that in order for our proofs to hold, that's a property that the shim has to guarantee. So remember earlier, yesterday we said, what do you need to actually run these systems, right? Remember we did the whole extraction thing, looked at the OCaml that got spit out. If I'm going to go run this, what do I need to do? Well, somehow I need to do some piping so that, you know, I sit and I read standard input, and when I see something on standard input or whatever, right, then I call the handle input message. And I also listen on some sockets. Whenever I get a message in a socket, I call the handle message handler, right? And it's just connected to that I/O. But actually, this means I need to do something more. Right? It means that I need to ensure that you know, the handlers never run halfway. Right? If I'm going to crash, I can't do it in a way that would be sort of halfway through a handler. And that is worth thinking about how to do right. And you can look at the Verdi runtime to see, you know, the things we do to try to mitigate those concerns. But the model is that handlers are atomic. There are no intermediate states. That's a tricky gotcha that you want to be careful with. Because actually, you know, the problem of distributed systems crashing in the middle of a handler is the kind of thing where things go wrong. Right? That's where people get in trouble. So you want to get that right. Okay, so let's move on to Verdi. So to start off with, just wanted to show something. First, I guess, are there any questions? Does the atomic thing make sense? Okay. Okay, so something that's familiar in Verdi, we also have the exact same kind of handler monad, right? Now, instead of being based on modules, we're going to have type classes for it that'll work for different types, but you know, it all kind of fits together. We have this function that produces you know, the type of a handler for certain parameters. We have return, which looks just like it did in simple DS. The order of some arguments is different, right? But it's all isomorphic. We have the exact same bind we were at last time, right? Everything works the same way. So hopefully, you know, starting off on the right foot. The thing that's more interesting in Verdi is this net module.